we have arrived at the last big piece of content that this course has to offer, which will be divided into 6 sub-videos, and everything that you've learned, almost everything that you've learned so far, will be clear as to why you've learned it in the next couple of videos. And first, we're going to talk about LTI systems. Now, what are LTI systems? An LTI system is called like that because it is a linear, time invariant system. And what that means, I will explain a little bit later, but every system is denoted with a T, or T1 and T2 and T3 if you have multiple systems. And into such a system we can give a function xt, we put it through our system and we get our output yt back. And there are some very important functions that go alongside this system, which I will explain in this video, and afterwards I'll talk about why we need these functions. So here we have our system T. Any function that we put in is called xt, and what we will get out is called yt. If the function that we put in is our step function, denoted by ut, what we get out of it is called the step response, or s of t. If our specific function is the delta t, so you can, if your xt, so if the signal that you input is equal to the step or the delta function, then it is actually not called y of t, but in that specific case it's called s of t, the step response, or the impulse response, h of t. Well, you're probably wondering, what are x, u, and delta exactly? How are these functions defined? Well, let's talk about that right now. Let's skip this one here. So, first, what does linear mean? If we have a linear system, that means that if we have a y of t, that is actually two functions, y of t1 and y2, y of t2, and it doesn't matter if we have obtained these y values by putting through our x functions separately, or that we have put them both together in our function, which is even the same as just putting the whole function in this. It doesn't matter if I split up a function into two parts and after I put them to the system, add them back together. That doesn't matter. That's what linear means. And for time invariant, it means that if I change the value in my output by some value, so I go through my function, it doesn't matter if I make that change before I go to the system or after I go through the system. So like this, if I change how my t changes in the x, before it goes to the system or after it, doesn't matter. That's time invariant. Well, now that is out of the way, let's talk about the step function. Our step function u of t is a simple function defined by the following. It is 1 if t is bigger or equal to 0, and is 0 otherwise. How does that look? Well, it looks like this. Here we have our t, and here we have our y, or our output. And the function goes like this. Let's take another color for that. This. At height of 1. This is the step function. It's nothing more than this. And this area, of course, goes on to infinity, but it is just 1 at 0 and 0 otherwise. And this output is, of course, called the step response because this is the step function. So, actually better denoted, the step response is equal to when I put the step function into my system. Now let's take a look at the other one, our delta function, which is defined as the following. It is infinity if t is 0 and is 0 otherwise. And this has some specific properties, because how we actually define the delta function, even if we draw it, it is just in the middle going to until infinity. This is actually defined as the following, our delta function. We have a box around 0, and the length of the box is defined as 2 capital delta, and the height of our box is defined as 1 over this 2 delta. So if we actually take the limit of our 2 delta going to 0, that means that the width of our function is lower, lower, and lower, and the height is going up, up, and up. But the surface of this function is defined as 2 delta times 1 over 2 delta, which is equal to 1. So because the width of our box is actually 0, its height will be infinity, but its surface, so if we integrate from minus infinity to infinity, of our delta function is still equal to 1. That is the important property that it has. It exists on one point, it goes to infinity, but its surface is always 1. And this has some other properties. Well, first is, of course, its impulse response, h of t is called like that, is if we put our impulse function through our system. And this impulse function has some other important properties. Namely, if we multiply this with a function at t, this is actually just equal to function at 0 times delta at t, which will be always infinity, except when you multiply it, of course, with a negative number, then it is minus infinity, or with the 0, then it will be 0. The second property is if that our delta function has shifted a bit. That means we're not looking at f0, but at that position that we have shifted. Then another property, if we integrate from minus infinity to infinity of our function times, that is a very ugly delta, of our delta function, this is equal to the value at 0, because what is the surface multiplied with each other? Well, it is what f0 is at that point, what the function is at f0. And with that, we also have the other definition that if we have shifted our delta function a little bit, this is just equal to the function with that specific value. And the last very important property, if we instead from minus infinity to infinity take from minus infinity to t from our delta function, but instead of t we take, for example, s, then we integrate up until t, and everything before this impulse function is of course 0. Its surface is there 0. When will its surface be 1? Its surface is 1 at exactly 0, when s is equal to 0. And after that, its surface is still 1 because we have gone over its surface already. So to visualize that actually is, if this here is our function, or how it is drawn, if we look at the surface up until this point, it is 0. If we look at the surface up until this point, it is 1. And that is how the integral is calculated. So if we take the integral from -infinity to t, then this is equal to actually our step function. Because if t is 0, then its surface will be 1. So our step function is actually which describes this behavior. So we know that the step function and the impulse function are related to each other because the step function is the integral or the integrated form of our impulse function. And these are 3 very, very important functions that we will use throughout the rest of the LTI systems because they are very, very important.